therefore I get minus this, which is fine. Okay, now we need to compute at the extreme of integration the value of these functions between square parentheses, and then I can write equal to, this is Ct plus, okay, if I substitute Ct instead of key, I get plus Cmax divided beta k plus 1 minus Ct divided Cmax to the power of beta k plus 1 minus, and then I have to substitute 0 instead of key, so minus, again, Cmax divided beta k plus 1, which multiplies nothing else, because this is 1, it's 0 here, and therefore between round parentheses I get a 1 to the power of beta k plus 1, it's still 1. Okay, this is the result of the integral, and I have the same factor here, which I can take as a multiplier, plus Cmax divided beta k plus 1, which multiplies this one here, 1 minus Ct divided Cmax to the power of beta k plus 1 minus 1. Okay, this is my result. There is, I think, a difference in there, because here I have somewhere a change of sign. So you can, of course, change the sign here, put a minus here, and then you change the sign here of, I forgot a square parenthesis here. This one was forgotten before. And you can change the sign of the two addendums between the square parentheses, the external square parentheses, the external round parentheses. But this is basically what we get. And then if we want to compute, do you remember Wt? Let's compute it. Wt is equal to Ct minus this one. And therefore, let's compute Wt. Because this was our starting point, we had Wt equal to Ct minus the integral, which is equal to Ct minus the result of the integral, which is down here. So minus Ct minus Cmax divided beta k plus 1, which multiplies, two parentheses, 1 minus Ct divided Cmax beta k plus 1 minus 1. Okay, and then these two eliminate each other, and then we can write in compact form. In compact form, we get Wt is equal to, let's change the sign now, because it's more practical to avoid a minus in front of the relationship. And then we get 1 minus Ct divided Cmax to the power of beta k plus 1. Good. This is our our target. Keep in mind that CT is, up to now, it's rainfall. And therefore you see that this is a perfect rainfall of model, because as time passes, you know CT, it's rainfall that you observed, and depending on time, you can compute what infiltrated into, what is the volume that infiltrated into the catchment, and by difference with respect to rainfall, you get the river flow. Now we have only one question left: how to write a computer code to apply this model. We have two questions left: how to write a computer code, and second question, how to include evapotranspiration, because we know that evapotranspiration, we need it. So we have to remove the assumption that evapotranspiration is equal to 0. I propose that we postpone to tomorrow. Tomorrow, please bring your PC, but we can dedicate tomorrow some, not sure. I decide tomorrow whether to dedicate 10 minutes to finishing here. Maybe that it's better to postpone it. The only issue is that if we postpone, the first lecture after tomorrow, if I'm not wrong, it will be in a long time from now, because next week we don't have any lecture, and the subsequent week I am abroad at a conference, and therefore we go after April 15, April 16, I think, it's the next lecture. So please don't forget about this, and I see whether tomorrow it's worth dedicating 10 minutes to, maybe, because I don't want to wait too long before seeing what is a possible code. And before we stop, I just wanted to make a final consideration. This relationship is quite, it's not complicated. If you compare it with the linear reservoir, it's something that looks more or less as complicated. It's not more complicated. The only thing is that we need to specify the value of two constants here, which are Cmax and beta k plus 1. And these are model parameters. What is a parameter in a relationship? It's a constant, meaning that it's not dynamically varying during the application of the model, but it's a constant whose value you can decide. So it's not dynamically varying, so we call it a constant. But it's a constant that you can fix. And the purpose of giving you parameters in a model is to allow flexibility, because by fixing the constant, you basically change the shape of the model. In the linear reservoir, we had indeed, even in that case, one parameter, which is k. And k is nothing else than the slope of the linear relationship between river flow and storage. So the relationship is still linear, because k is a constant. But if you vary k, you change the slope of your linear relationship. In the same way here, you may change Cmax in order to adapt the model to a catchment which may have a higher potential storage with respect to others, and you may change beta k, and we know already what is the effect of varying beta k between 0 and infinity. So the consideration is, look, we have already one more parameter here with respect to the linear reservoir, and we are not done with the model yet. We will see that there are more parameters that will be introduced. More parameters means more flexibility. You can understand it. If the purpose of the parameter is to provide flexibility, if you have two parameters, you have twice flexibility with respect to the linear reservoir. But on the other end, parameters need to be estimated, need to be calibrated. How how we say in numerical computation, which means an additional complexity. So we will need to discuss what are the parameters to be calibrated and how to calibrate them. So far, we found out 2 parameters that need to be calibrated. Okay, see you tomorrow, and bring your PC, please.